Hello everyone. So, we will continue with the textile reinforced composite. In last class, we have discussed the critical length, and now we will discuss how to calculate the modulus and ultimate failure stress of continuous fiber composite, like unidirectional modulus and ultimate failure stress of composite, knowing the stress strain characteristics of both matrix material and the reinforcing material. Here the assumption is that the fibers are in continuous form, and as it is continuous, so strain along the longitudinal direction for both the matrix and the fibers will be same as that of the composite. So, epsilon m is the strain of matrix, epsilon f is strain in fiber, and epsilon c is strain in composite. So, stress can be measured by multiplying the modulus with the strain. So, total force is normally it is addition of the force on fiber and force on matrix. Now, if we know the volume fraction of fiber, we can calculate the required or calculated the stress and calculated modulus of composite. So, for unit cross sectional area of composite, so stress on composite is equal to stress on fiber plus stress on matrix. If the volume fraction of the fiber is V f and volume fraction of matrix is V m. So, the equation is the stress in composite equal to stress in fiber multiplied by volume fraction of fiber plus stress in matrix multiplied by volume fraction of matrix. Similarly, we can get the modulus of composite by multiplying the individual fiber modulus with the volume fraction of fiber and modulus of the matrix with the volume fraction of matrix, which is 1 minus volume fraction of fiber. Here in this equation, so Poisson's ratio is not considered. Now, we will take the example of two situations. One is the composite with the ductile matrix, another is with the brittle matrix. So, composite, as we know, two major components, one is matrix, another is the reinforcing material, that is in case of textile based composite it is a fiber. Now, here if we see, for example, here the two stress strain curves are given for fiber and matrix. Now, from this figure we can see the breaking stress of fiber is 2500 megapascal and breaking stress of matrix, ultimate stress of matrix is 1300 megapascal. As the matrix elongation, so breaking elongation is higher than the reinforcing materials elongation. So, they will not break at the same time. So, while extending, although fiber, the reinforcing material is taking maximum load, but due to its lower extensibility, so lower breaking elongation, fiber will break fast. At that time the load on matrix, matrix will carry load, it is less than the breaking stress of the matrix. So, that stress on matrix will be 1200. So, this is just typical example how the calculation will be done. 2500 is the ultimate stress of reinforcing material, 1300 is ultimate stress of matrix, and 1200 is that the stress carried by the matrix when the fibers are breaking. So, this is required to calculate the critical volume fraction. So, ultimate strength of composite is sigma u c, ultimate stress, which is the addition of the stress by the fiber and stress by the matrix. So, we will consider two different situations, a ductile material where the ultimate strain of fiber is less than the ultimate strain of matrix. This is the diagram. Here matrix is the extension is high, this is ductile composites figure, and we can have another composite which is brittle matrix. Typically the brittle matrix are the thermoset matrix, where the matrix material, matrix elongation, the strain, breaking strain of matrix is less than the breaking stress of, so breaking strain of the fiber, reinforcing material. Now, for ductile material, if we see here as per this picture, this is the stress strain stress strain curve of fiber, which is reinforcing material, and here is the matrix. The ultimate strain of matrix is more than ultimate strain of fiber. That is why it is called ductile matrix. This is the stress of ultimate stress of fiber, and this is the ultimate stress of matrix, and here sigma dash m. Sigma dash m is the stress on matrix when the fibers are breaking, because matrix is having higher breaking stress. So, in this condition we will consider two different situations. In situation 1, before the fibers are breaking, the load will be carried by both the fiber and the matrix. But after the fibers are breaking, during this stage, when fibers have broken, the load will be transferred to only on the matrix. So, let us see the situation before the breakage of fibers, because fiber will break fast. In that case, ultimate stress of composite is given by the ultimate stress of fiber, because fibers are breaking, ultimate stress of fiber multiplied by volume fraction of fiber, plus this is the stress carried by the fiber, and at that point the stress shared by the matrix is sigma s sigma dash m, that time multiplied by volume fraction of matrix. In this situation is before the breakage of the fiber. So, both fiber and matrix they are carrying their load, but after the fibers are broken. So, all the fibers are broken. So, after breakage of fiber, the load is shared by only the matrix. So, then ultimate stress of composite will be the multiplication of ultimate stress of matrix and the volume fraction. The plot here is that with volume fraction of fiber at starting point in x axis, at the starting point the volume fraction of fiber is 0 and its maximum volume fraction of fiber is 1. So, when volume fraction of fiber is 0, that means V f is 0, the ultimate stress by this composite is, it will be equal to sigma dash m, which is this starting point, this solid line is showing. So, at 0 we will get a point, this is the point equal to, it is a sigma dash m is the starting point. This is matrix and here in this situation, if we draw the ultimate stress of composite versus the volume fraction, this is volume fraction of fiber. At this point the volume fraction is 0, here volume fraction is 1. So, here volume fraction is 0. So, at volume fraction 0, as per this equation, let me draw the equation composite. Because when the fibers are breaking, the matrix is carrying sigma dash m. Here if we put the V f equal to 0, so this will become 0 at 0 volume fraction and this will become 0. So, it will be effectively sigma dash m. So, before fiber are breaking when this equation is followed. So, this is m. At 100% fiber volume fraction, say volume fraction is 1. So, if you put the V f equal to 1, here V f equal to 1, then what will happen? This segment, this section will be 0, because 1 minus 1 equal to 0. This will become is 1. So, at this is the point. So, if we join, we will get a plot which shows the ultimate stress of composite when the fibers are not broken. So, when the both the composite, that reinforcing material and fibers, they are carrying load. But in case when the reinforcing materials, they have been broken, in that case the ultimate stress of composite will be equal to ultimate stress of matrix multiplied by volume fraction of matrix, that is 1 minus V f. Here if we see at volume fraction of 0, so V f, if we put V f 0, then this will become sigma m. So, this is u m. So, this will become sigma u m. Okay. So, this is equal to this point. And for 100% volume fraction, when there is no, theoretically there is no matrix, 100% fibers are there. So, this value becomes 0. So, this total ultimate stress will become 0. So, we can, if we join, so we can join with the different color. So, this curve is showing the ultimate stress before the breakage of fiber, when both matrix and fibers are taking load, but this curve is showing the condition where matrix only is taking the load. Okay. So, if we see that at this joining point, this intersecting point, the volume fraction, it is known as critical volume fraction of fiber. This is the critical volume fraction of fiber. So, V critical, so this is the joining point. So, before the, if the fibers which we use, if it is less than the critical volume fraction, fiber volume fraction less than the critical volume fraction, then this equation will follow, and if it is more than critical volume fraction, then this equation will be dominating. So, we must use the fiber volume fraction more than the critical volume fraction, then only we will get the assistance of the reinforcing material. So, this from here we can calculate the critical volume fraction. So, if it is less than critical volume fraction, if we use the fibers, smaller quantity fiber, then we will see ultimate stress of composite will be dominated by the matrix only, not the fiber, because we can see here. So, at lower level, less in this zone, the matrix, the composite stress will be higher, because the stress of composite at any point along the axis, at any level of volume fraction will be the point where among these two equations, two curves, whichever is higher. So, if the volume fraction is less than the fiber volume fraction, sorry, critical volume fraction, then this equation is dominating. Similarly, for brittle matrix, the treatment will be in a similar way. The matrix is brittle. So, both the stress, breaking stress and breaking strain are less than the fiber breaking stress here, ultimate stress again it is at this point, matrix breaking stress is at this point here, and during the breakage of matrix, the load carried by a fiber is sigma dash f, and similarly we can get this graph where it shows that for brittle matrix, if the volume fraction is more than, that is critical volume fraction, then majority of the stress will carried by the fiber, which is strong enough, which is reinforcing material. So, ultimate stress will follow this equation, that is the stress of fiber. So, it is ultimate stress of fiber multiplied by volume fraction, that will be the ultimate stress of composite. So, from these two figures we can calculate the volume fraction of both brittle matrix composite and for ductile matrix composite. Here we can see the volume fraction selection is extremely important. We should know the volume fraction, and accordingly we have to decide the fiber volume fraction. So, critical volume fraction is important. So, based on critical volume fraction, we should decide the proportion of fiber, the fiber volume fraction, it should be more than the critical volume fraction. Now, we will discuss here the composite manufacturing processes. There are different processes available. Most of the commercial process we will see at existing process, they are based on the thermoset matrix, and obvious reason is that thermoset matrix is the viscosity is less. That is why most of the existing manufacturing process it is based on thermoset matrix, and thermoplastic matrix for composite making from thermoplastic matrix it is very difficult. For that we need specialized system, and those processes where we can use the thermoplastic polymer as the matrix material in a composite, we will discuss in next class. Here we will discuss all the manufacturing processes based on the thermoset matrix. First process is the hand layup process. As the name implies that hand layup means it is manually we have to mix the matrix with the reinforcing material. Here we can see, here the person is laying up the thermoset matrix, which is with a low viscosity. There is a frame over which that this is the glass fabric, and the fabric is laid on this frame, and the matrix is laid on the poured on the this glass fabric, and the matrix penetrates into the glass structure and forms the composite. Here the resins they are laying up, and after doing that manually they will press it by some rollers, so that proper penetration of matrix takes place. As we can see from here, the tooling cost is low, because there is no specialized machinery required. Versatile products can be hand laid. This is hand laying. So, any sorts of products can be made, because we have to only lay the reinforcing fabric and pour the matrix, thermoplastic matrix. The main disadvantage of this process is that it is a long curing cycle. We have to allow time to get the matrix solidified. So, it is time consuming, high labor demanding, because you need large number of manual labor, because here we are pouring the matrix, and by hand we are trying to penetrate that matrix material. There are chances of the air bubbles in the final product, no control over orientation of fibers. If we try to use the loose fibers, then we do not have any control, but in this picture we can see it is a glass nonwoven fabrics are used. So, it is difficult in ensuring consistency in application of resin, because it is manually done. So, the resin concentration at different places may be different, large void content due to the air bubbles which affect the quality of the matrix, and most important is that it is not covered. So, liberation of volatile organic compound which may be harmful for human health, the chances of this human health hazard is there, but the advantage is that it is a simple process. Next method is that spray method. Here instead of hand laying, we spray with the help of spray gun both the chopped fiber and resin. So, we can see here from the, suppose this is the shape we want, okay, and we are trying, this is one spray gun and the chopped fibers are, these are the chopped fibers are coming, and we can use spray of the resin. So, these are laying here and that can be laid and we can form the composite. So, this type of composite formation is there. So, the composite manufacturing process is known as spraying method, where chopped fiber and resin is sprayed on a mold. This combination is then cured. This process is slowly substituted by the resin transfer molding. So, because of the obvious reason here, the chances of the air bubbles are there, void content is high. So, in RTM resin transfer molding, the chances of void content is less, but still due to its simplicity, due to its flexibility, we still use this spray method. So, the main advantage of this method is that any material can be used as mold. So, we can have very complex molds shape. It is a continuous process, not like hand laying method. This is a continuous process, because the spray gun, it can run continuously, and in case of any correction required. So, in case of any void content or any uneven thickness, respraying can be done to correct any error. The disadvantages are that its process is unfriendly to environment, as we have seen in the hand laying method, because the volatile material can get evaporated and mix with the environmental air. Inconsistency in fiber and matrix distribution, because they are indirectly laid. The mixing is done indirectly through spraying method. So, there is a chance of inconsistency. Fiber orientation, it is not being controlled. We cannot control whatever fibers laying are there. So, if we want unidirectional orientation, it is not possible, because fibers are deposited with the help of spraying gun. So, that is why we cannot control, it is a slow process. Here we can see that if we want the smooth finish in both the sides, it is not possible. Only the side where the mold is there, the smooth finish is there, but other side it is randomly deposited. So, there will be some randomness in the surface. Next method is open mold spray up chopping method, where the rovings or fibers are chopped first and then mixed with the matrix material, because it is a similar to the hand layup, but it is a quicker method, and we can develop a complex shape of composite. Thickness and consistency is controlled manually here. The process is more operator dependent than hand layup, because here the operator has to control both chopping and the spraying. So, these are used for production of boats, tanks, transportation components. So, the main advantages are the process is simple, the process is high potential to automation, very large parts can be produced, tooling cost is lower, on-site fabrication, that is more important. See, in on-site fabrication, so if we want to fabricate some composite on site, that we can do by using open mold spray up chopping method. So, here we can see here, and suppose roving, this is roving package, this say glass roving or anything, here there will be chopping, it is chopped, and then this is a resin, and this resin here is pumped with the help of pump, and there will be a gun, spray gun, and then there is a mold. Suppose this is mold, and suppose this is resin material and they will be mixed here and it will be formed, the composite will form here. So, the chopper gun feeds glass roving and resin. The resin saturated this chopped glass is then deposited on the mold. The laminate is then rolled to thoroughly saturated glass strand and compact the chop. So, that then there will be one roller which will compact the matrix and the glass fiber. To achieve the desired thickness, additional layer of chopped laminate can be added. So, we can keep on adding to have required the thickness. Next is the sheet molding. Sheet mold composite uses the chopped glass strand as reinforcement and polyester as resin in the form of a sheet. So, where we will get a sheet, so in between the two sheets, that is the protecting sheets, the chopped glass fiber and polyester resins are placed. In this process, chopped glass strands are packed between two layers of film. So, two films will be there. These films are used just to separate the layers. This sandwich of chopped glass strand and film on which the resin is applied is made to pass through a compacting system that ensure the complete penetration of resin into the reinforcement. Now, let us see, there will be typically two films. Now, this is one film is coming. Okay. Now, here we are applying some resin one side, this is resin is applied in this side and some knife will be there, doctor's knives, which will control the resin thickness. And another it is coming here with the resin. Okay. And this side it is a resin side. Another film, suppose this I am drawing with the dark blue color, this another film is coming where again the resin is being applied on other side and in between two layers, in between two layers. So, this side is, so this is resin, here this side is resin impregnated. Now, in between these two there is a glass, these are the glass rovings and these glass rovings are chopped here and they are mixed here. So, in ultimately what is happening, there will be one layer at the top, this layer and this layer at the bottom. This is impregnated with resin, this side is impregnated with resin and in between there will be glass. this is one prepreg and then they are passed through the roller or under pressure, they will get compacted, the resin will penetrate inside the glass, they will get mixed, and till this time the resin is in viscous form. Before it gets solidifies, we can form a roll and keep it under cold condition. When we require to form the composite, we can take it out and solidify depending on our requirement. So, these are put on storage for few days before final molding to will let the prepreg thickness, it will get gradually it will thicken, because with the time the viscosity of the resin will increase and then gradually it will solidify. The film's function is that to separate two layers, when we form roll they will not get stick to that, to each other. So, the advantages are high throughput, inexpensive, and the process is reliable because we can get sufficient uniformity. Main disadvantage is that high volume fraction are not possible because of the fact that the proper penetration is required, and that is why if we use high volume fraction of fiber, then proper impregnation will not be possible. The another advantage is that we cannot, as the process says, we cannot form any complex shape. Here plain sheet or plain board can be made in this process, because it is a sheet form. Third process is that next process is the bulk molding. Here the fiber volume fraction of 50% can be achieved. We can have finish application, excellent mechanical properties can be achieved. The system is very simple here, and this in this system we have to use the chopped fiber of the smaller length, the chopped fibers and the matrix that prepreg, these are the fibers, and the matrix material, they are mixed together and they are fed through the hopper. This is a prepreg, and there is a screw arrangement. This is the screw arrangement. With the rotation of screw, this prepreg will be pushed in one direction, and there is a mold. This is a mold of a known shape. This is a mold where if we want a particular shape, suppose we need a particular shape, this type of material if we need, we can. So, this is the shape we final shape we require. So, here due to the screw arrangement, this prepreg will be pumped inside the mold. And ultimately this will form the composite, required composite. And here the chopped fibers and the resin are mixed. So, only short staple fibers can be used, as has already been mentioned. So, continuous filament or long fibers we cannot use, because long fiber if we try to use, so fibers, even staple fiber with longer fiber length, then proper mixing is not possible. So, fiber arrangement cannot be controlled, complex parts cannot be manufactured, and this process requires high temperature as well as high pressure, because here we have to apply high pressure. In this method, bulk molding method, we can use the thermoplastic matrix also in the form of say powder. So, for that high temperature is required in the mold. Next system is that resin transfer molding. Here there will be a mold cavity, and into the cavity of the mold the resin is infused at high pressure. Now, this is the mold. Okay. This is one side of mold. Suppose we want to hemispherical or curved shape matrix, sorry, curved shaped composite. This is the shape. Here inside we have the reinforcing material. It may be textile fabric also, nonwoven, and there will be one opening for resin injection. Resin is injected here at high pressure, and from the side there will be sealing and everything will be there, and resin is injected at high pressure. And in this system only thermoset resin can be used. Due to its low viscosity, they will penetrate into the inside the structure of the textile material, and after curing this molds, this is the one side of mold, this is a male mold, if you see it is a female mold. So, after that we can remove the mold to get the composite. So, prior to closing and clamping of the mold, the reinforcement is stationed in the mold cavity. So, that mold cavity reinforcement is already placed there. So, resin is injected under pressure. So, we need high pressure for higher viscosity resin. So, pressure can be controlled here, and after that the part is cured. The reinforcement used can range from preform to a pattern cut roll stock material. So, it is a versatile process. The cost of composite manufacturing is low here, So, low tooling cost, low void content, because the composite that the matrix can be injected at high pressure. So, void content is low, low pressure injection. So, for low, very low viscous material, so injection pressure is required low pressure. So, high volume fraction can be achieved. So, as high as 65% volume fraction can be achieved. So, limited volatile emission, that is important in hand layup or open mold system. So, this the volatile emissions were there. So, RTM is environment friendly. Here good surface finish can be achieved on both the sides, because both the sides are covered. There are other advantages. So, complex structure can be produced, even hollow shape can be produced if we can manufacture the mold. The main disadvantage is that the intricate parts are difficult to produce. So, simple shape, hollow and other shapes, simple shapes can be produced. If we try to produce a intricate part, so this method is not suitable. So, material wastage sometime takes place due to the leakage, and higher curing time is required. These are the disadvantages some. And compression molding is basically it is a simple technique, but in compression molding normally we use the thermoplastic matrix. The main advantages are its consistency, here the system is that there is a mold. So, we can have a mold of any shape, okay. This is a mold, and at the top there will be another mold. So, after that we can lay the reinforcing material along with the, this is the say one layer of matrix, this is reinforcing material, then we can put another layer of matrix, another layer of reinforcing material. So, we can do many combinations, and at the top there will be the other part of the mold. Okay. Now, this is the base mold, and under high pressure this is pressed, and then the heater is on. This is basically these are the heaters, there will be heat. So, at high temperature this thermoplastic matrix they melt and mix up with the penetrate inside the reinforcement structure. So, it is a very expensive, because mold cost is very high. So, heating up and cooling down of the machine is time consuming. So, as I have mentioned, molds are expensive, but the system is very simple. Next process is the prepreg manufacturing method. In the prepreg, the reinforcing fibers are impregnated inside the resin, that mainly thermoset resin, and then they are rolled, but before rolling from both the sides 2 layers of the separating films are there. Suppose this is a reinforcing fiber, or we can take the fabric as well. This is now this reinforcing material, it's passed through resin. So, they are getting impregnated with the resin. So, this is the prepreg, and this prepreg we have to maintain. We have to, this is resin impregnated fabric, and this prepreg we have to form a roll, but we cannot form roll because they will get the next layer will stick to the previous layer. For that, the system here is that the separating film roll, this is a separating film from both the side, there will be 2 separating film. So, this film is there, and here in between there will be prepreg, this is prepreg, and then we can form roll of this, we are forming roll, and these films are separating film. So, here control over orientation of fibers are there, which is very important. We can use filament, so continuous filament sheet we can use woven fabric, we can use non-woven fabric as the reinforcing material. Here uniform distribution of fiber and resin is there, because the reinforcing material is dipped into the resin. So, resin that it will be in uniform, low void content, completely immersed, because the reinforcing material is completely immersed inside the resin. It is consistent, low curing time, high throughput, because this is continuous process. The main disadvantages are, as the process is continuous, the production will be high. So, large order is required, otherwise this is not suitable for the batch wise production, it is a continuous production. And at the same time, if we produce large quantity with the thermoset resin, if we keep for long time, then this will get solidified. So, we have to use the this prepreg before it gets solidifies, and otherwise we can keep it under refrigerated condition where temperature is around minus 80 degree Celsius. So, that adds to the cost. So, if we keep at room temperature, this prepreg will get solidified and that will not be useful. Next is the filament winding technique. It is a simple technique where the filaments are wound on the one cylindrical shape package, and before winding these filaments are passed through the resin. This is the cylinder, okay, and which we can, which rotates, rotating cylinder. Now, the packages are there, the reinforcing materials packages are there, and these are So, number of packages we can take. These filaments are coming and then they are processed through the immersed through the reinforcing material, then like it is a resin, and this resin immersed filaments are then wound on the cylinder. The resin immersed. So, the filament along with the resin, they are winding on this package, this cylinder, and here after winding they get automatically solidifies, because the resin is thermoset resin, and after solidification we can take out from the package this base cylinder. So, this will ultimately form a cylindrical shape composite. This composite will be hollow cylindrical shape. So, if once we take out after solidification, and there will be one traversing mechanism depending on the shape required or depending on the thickness required, we can change the traversing speed. So, here in textile manufacturing process can be used, normal winding process can be used here, only hollow parts can be produced here. We cannot produce any other part. So, main disadvantage is only cylindrical shape can be produced here. So, high speeds is not possible because the matrix has to be that reinforcing material has to be impregnated with the matrix properly. Curing by heat is not easy to apply, because from inside there will be that basic base cylinder on which the filaments are winding. So, heat application is not that easy. So, curing time will be very high. Next method of manufacturing, which is simple one, is it is known as pultrusion. Here in this case only continuous filaments can be produced. So, continuous filament as reinforcing composites are produced, like earlier one, that is the filament winding technique. The pultrusion, the term came from the pull and extrusion. So, here the material is pulled through the die, that the resin impregnated filaments are pulled through die to form the composite. The shape of the or cross section of the composite is controlled by the shape of die. First there will be large number of filament packages. So, these are the filaments. Depending on the requirement. So, these filaments are then taken together. So, to form a thick toe, then they are immersed into the resin. The resins are there here, and then this thick filament immersed with resin there will be one die, this is the die shape, they will be pulled through this. So, this is the die shape, and these filaments will then be pulled through this die to form a required shape of composite. So, this is the reinforcing material shown in red. So, we will get the composite, but here we need one pulling arrangement. So, maybe roller pulling or maybe other type of pulling. We have to pull the reinforcing material through the die. So, continuous fiber reinforced composite is produced here. So, the manufacturing process is similar to extrusion, in which molten plastic or metal is pushed through the die, but here the reinforcing fiber filament along with the resin will be pulled through the die. So, the main advantages are the continuous reinforcement, the labor requirement is low because the moving parts are less, the process is mostly automated, variety of cross sections can be produced depending on the shape of the die, high throughput, the productivity is high. The main disadvantage is that here mainly thermoset matrix can be used. As I have already mentioned, die cost is very high, and another point is that die can be easily clogged, because the composite, the matrix, thermoset matrix deposition may be there in the die. So, it can be clogged easily. So, we must take care of cleaning it frequently. And the last method is the vacuum bagging method. In this system, we do not use any external pressure for compaction. On the other way, we create vacuum, so that the atmospheric pressure, with the help of atmospheric pressure, the impregnation and the compaction takes place. So, here the impervious bags are placed, so that the films are laid on the composite material and the air is evacuated. So, suppose this is laminate of reinforcing material, and we have placed the resins also, immersed in the resin. Now, in this laminate what we do? We are placing different layers. The layers are the bleeder layer, this is the bleeder layer which will absorb excess resin, then releasing films are there, there will be releasing film. So, different layers are put on, they have their different functions. Now, at the uppermost side there will be a bag, a sheet material, okay, and this is placed in such a way there will be a gap through which we can take out the air. So, this is air is taken out. So, as air is taken out, this will get compacted due to the atmospheric pressure. and the composite will get compacted, compressed, and finally, the whatever voids are there, the air bubbles will come out and composite formation will complete. So, air is evacuated from the bag and the composite is consolidated under pressure of 1 atmosphere, because it is a atmospheric pressure is required. The application of pressure ensures the impregnation of reinforcement with the matrix. So, and there will be uniform pressure, because the total air is evacuated. So, uniform pressure will be applied throughout the composite. So, main advantages are the superior quality products can be obtained, versatility in use of fiber matrix combinations, but here we can use only the reinforced, that is the thermoset matrix, but different types of fibers can be used. It is very simple, one can easily design this type of manufacturing method easily, it is a low cost. Main disadvantage here, this the pressure we have to depend on the atmospheric pressure, more than that we cannot insert. So, very low speed, because we have to form the total system for a particular shape of composite, it is not continuous, requires frequent replacement of bleeder cloth, because this will get saturated with the resin. Heating capacity is restricted due to different layers, the heating is not easy. So, matrix reach and matrix stub areas are possible if proper care is not taken, because we are not adding any extra matrix material, we are only here, it is a compression system at low pressure compression system, that is why chances of matrix reach and matrix stubbed areas are there. So, we must ensure proper impregnation of reinforcing material with the matrix material. So, these are all about the manufacturing methods of composites. In next class, we will discuss the textile structures in advanced composites, mainly prepreg formation and preform formation, where we will see how the thermoplastic matrix are used in composite manufacturing. Till then, thank you.